technical glitch here. So good morning, everyone. Finally, AGN talk. So I'm going to shift the gears a little bit here and talking about radio AGN, and in particular, young radio AGN, and some of the amazing science that ngVLA and SKA can do for this subpopulation of radio AGN. So let's get started. So what I'm showing here is our current understanding of the cycle of radio jets, or jetted AGN. That's the term people would like to call it now, rather than radio loud. So basically, when we started observing with early radio telescopes, these giant radio galaxies were the obvious sources that were detected. Along with that, we did have this unique sample of compact and as well as peaked spectrum radio sources that were also observed even with the early telescopes. And the follow-ups had shown that, in fact, these were baby FR1s and FR2s, or these young radio AGN. Not all, but many of them were, in fact, found to be such, in this youth of the radio galaxies. And with time, we have sort of realized that the jets do follow this cycle. Sometimes it becomes a cycle, sometimes it's not. Is that once the jet production stops, you go into this very, the lobe starts to cool off very rapidly, and you start seeing this remnant. And some accretion event, if it takes place, you do get to see this restarted AGN. And some of our, I'm showing some example from amazing LOFAR images that are being just the key telescope for detecting and understanding this duty cycle of radio jets in general. So the focus of my talk is going to be just talking about this young and compact radio AGN, and what are some of the key science we could do just to get started once ngVLA and SKA comes into their full capabilities. So just a little bit of a definition, what do I mean by young radio AGN and some of their key characteristics that are useful. So here I'm summarizing them in this plot. On your right is, sorry, from my side, on your left is the linear size versus radio luminosity diagram, which is a key diagram, and all of the radio jets, once the jets are produced, the lobe start to expand, and they follow a particular track here. What do I mean by young is when the jets are still within the galaxies or host galaxies, so they have linear sizes of about 20 kiloparsecs or less. And overall, there's an increase in luminosity as jets go from this compact parsec scale sizes to become FR1s and FR2s. The other key property of these compact AGNs are their evolving radio spectra. Radio spectra, when sources or the lobes are on the compact scale, do show this characteristic feature, which is the turnover. And this location of the turnover is inversely proportional to the size of the lobes. So when you have very compact scales, the turnover is going to be at gigahertz to hundreds of megahertz frequency, which is where we have our, which is the part of the sky that we can observe with radio telescopes. So, and in fact, this has been the key way to identify different samples of peaked spectra, and also filter out some of the young radio AGN candidates from these samples. So here are some of the key questions. Young radio AGN in general, or compact radio AGN, have been some of the, it's one of the least understood population, just because of the limitation of current instruments. With new telescopes such as LOFAR, GLEAM surveys, and ASKA, we have just started to understand how common is this phase of compact and subgalactic radio jets. So the big question we still don't know is how common they are, and we have just begun to answer the question. The next two questions are kind of related. First of all, what is the energetic impact of jets on its surrounding medium? And then it ties into the big question of galaxy evolution, is whether in fact whether this jet can interact with the host galaxy, and then whether it's capable of doing this AGN feedback, which is jet-driven, and impact the star formation and the growth of the host galaxy. So let's start with the first question, is to identify how common is this compact phase. And that goes to the question of how do you identify compact and young radio AGN? The reason being, it's a very short phase if you just look at the overall timescales. So it can be difficult to identify large samples of such sources. The obvious way would be to just detect morphology. You need sub-arc-second or milli-arc-second resolution, depending on redshift, and also the size scale that you want to pick out. But this is an impractical way of identifying because you know that VLBA mapping or even sub-arc-second mapping of the entire sky, a large portion of sky is going to be difficult. And that is the reason the identification using this spectral curvature or this peak spectra has been the most popular way of identifying radio-selected samples of compact AGN. And with multi-epoch surveys, nowadays we have in fact we are able to identify some of the most compact and youngest phase because some of these sources are dynamically expanding within the timescales of a few decades or so. And here I'm highlighting work by Christina Nyland, where she has a poster talking about this sample, which was detected in VLAS, and some of her sample are restarted, and some of them are really young radio AGN. And I highly recommend you to look at her poster. Poster is P52. Yeah, so let me just talk about a little bit of identification that we have been doing using latest surveys. We have been identifying peak spectrum sources using surveys for many decades, but because of this wide spectral coverage that the new surveys are providing, we are able to identify sources over a range of ages and luminosity. The reason being, I just showed you that the spectra of a source evolves as it becomes from it grows from younger phases to older phases. And depending on where your survey is located, you are likely to be sensitive to sources that are peaking within your frequency of the survey. And this is the figure on the right. It sort of explains the fact. So depending on different surveys are going to identify different populations. And here is one example of using surveys in-band spectral index to identify this peak spectrum sources. And some of the samples were identified using GLEAM and LOFAR surveys in recent few years. The other ways is that there's a way of selecting sources using just the radio, but with complementary multi-wavelength surveys, you are going to find many, many other samples of radio blind selections of AGN. And if you're coming in from multi-wavelength, how do you go on using radio surveys to take the full advantage of understanding the incidence of radio AGN and compact radio AGN in general? And this is where I'm just highlighting some of the work that I have done for heavily obscured quasars. Is basically you can take advantage of all of the radio surveys that are available now and that will be available in future to construct a radio spectra just to pick out some interesting sources and just get a better handle without having to request a full multi-frequency imaging to characterize the spectra. This can be complex because of the variability that is associated with it, but it's just one step to get into understanding incidence of radio AGN in your sample of multi-wavelength selections of AGN. I'll talk about the sample that I worked on in this example in a bit. So as I said, we've just begun to understand this, and I wanted to highlight the contribution from SKA here, because SKA's resolution in its main design might not be enough to resolve out these subgalactic sources, in particular at high redshift. But in fact, its spectral coverage is going to be very key to identify complete samples of these compact and young radio AGNs. We can, and because of its sensitivity, we can go up to very low kinetic jet powers. And this is something we still don't know how common it is and how common the compact sources are even at lower jet luminosities. So this is where surveys, deep and wide surveys with SKA are going to be very key to understand this, to find more and more complete samples of peaked and compact radio AGN. So now in the last few minutes, I'll talk about some of the case studies that you can do. As I was mentioning, There are going to be many surveys which will identify different AGN. Here, I'm just going to show a case study of what I have been doing with my PhD and how I have utilized different radio surveys to understand incidence of young radio AGN in this sample, and how ngVLA and SKA can help us push this kind of studies further. So a little bit about the sample that I have been working on. It's a sample of heavily obscured quasars, which in fact was selected using WISE and NVSS. The way the heavy obscuration in the WISE has been done, we have sort of have the understanding now that these WISE selected heavily obscured quasars are in fact probing this very unique phase post-merger, where AGN is undergoing its very peak fueling activity, and if jets are present and subgalactic, they have just started to, they're likely to be interacting with the host. And the goal for this sample, which we found at redshift of about 2, was to sort of identify interesting sources for which we can go and do some detailed follow-ups to understand AGN jet-driven feedback and jet-ISM interactions. So we started with a snapshot observation with VLA. The goal was to identify how many of our sources are in fact subgalactic. And what we found with our snapshot imaging was, in fact, most of these sources were compact. And at redshift, even sub-arc second resolution is not enough. It will just give you a limit of 2 kiloparsecs. And you really need to go to milli-arc second imaging to look at the radio structures that are within the host galaxy. And I just showed you about how you can utilize broadband spectral modeling, combining multi-epoch surveys to look at the radio spectra, and in fact found that majority of our sources were having this characteristic peak turnover and making them good candidates for possibly young radio AGN. And the next, so this is a work in progress that I'm trying to understand, is that we do have some interesting sources in this sample, and what I'm doing with our deeper follow-ups is trying to understand the impact of jets on its ambient medium, or impact of lobes on the surrounding medium, and possibility of jet-ISM interactions. So to characterize this impact of jets, we really need deeper high-resolution follow-ups. And this is a work in progress, so I don't have any results. But what we are doing is we have picked up some interesting sources and obtaining observations with VLA using multi-frequency data. So just to give you numbers, we observed for 30 sources, and we needed about 100 hours of VLA to get L to KU band frequency imaging. And there was really not much more we can do with this kind of sources. And these are radio intermediate in the luminosity. And in fact, if you want to actually resolve some of the most compact sources in this kind of sample, we had to go to VLBA. And you can see on the right are some of the VLBA images at the bottom. We only observed for 12 sources, and we needed 80 hours of VLBA time just to do that. And even with that, we are not, the kind of details you see with FR1 and FR2 galaxies, just, it's been quite difficult to do with current instruments that we have available. So I just wanted to highlight the ngVLA's role in sort of revolutionizing this high resolution or the resolved mapping of the radio lobes or radio structures in the case of young radio AGN. Here is a figure that's taken from Christina's white paper, talking about ngVLA's role in doing AGN feedback. There's going to be, basically ngVLA is going to allow us to do this sort of mapping because of the sensitivity improvement over JVLA. We can do this kind of mapping for a large samples of radio AGN and with much more ease. And just within a few hours, you can get to this kind of details even for compact AGN. And the more interesting thing that I am excited about is the long baseline array, which is the ngVLA's extension of VLBA. Because with VLBA, we could just do 80 hours, in 80 hours, we could just do 10 sources, and with ngVLA's long baseline array, with the sensitivity with the improvements in sensitivity, we are able to do, we will be able to resolve jet morphologies for redshift of 2's type of sources with very much ease. And this is how you can quantify the structural, spectral, and polarimetric information and energetic information in these type of sources. I am out of time, so I'll just talk about one of the other key signs that ngVLA and SKA will both play a crucial role is looking into this question of what causing the turnover. This is a long debate that's going on, and we just need a deep sub-gigahertz data with high spectral resolution to sort of map out the turnover part of the spectrum to know what's going on. And this is where the SKA's spectral coverage and sensitivity is going to be really useful. I did have a slide, but I'm just going to skip that. But just the point, I'm just going to keep it here instead of summary to tell you that there was a really nice introductory talk today talking about going from just characterizing jets to understanding ISM, and we can do with combining different telescopes, and then get to this question of AGN-driven feedback as well with ngVLA. And with that, I'll wrap up, and thank you so much.
Thanks, Pallavi. Do we have any questions? Yep, over here.
Can I start? No. Okay, thanks for a great talk. And I'm really glad that you mentioned the long baselines for the ngVLA. And I think it's particularly interesting that when one wants to do a proper motion study of the hotspot advancement, then going to high frequency is now very challenging because the spectrum of the hotspot is typically steep. And so it's really hard to get high resolution. But if you have a great sensitivity instrument, then you can do this study at high resolution. So your beam becomes smaller and you need a much shorter time baseline to detect the proper motion. So I'm not sure if you have any estimate of how many candidates or sources you could do a kinematic study to actually determine their age, but that would be extremely interesting and promising, I think.
Yeah, that's actually really, I don't have estimates of what luminosities you could do this for, but yeah, you've raised a really interesting point that I haven't included in my slides, but yeah. So far we were able to do this with VLBA of doing the kinematic motion, actually seeing the jets move, or the hotspot move with time. But yeah, this is something we can easily do with ngVLA and the long baseline array with just an improvement of sensitivity. But I haven't done the calculation as to what are the exact luminosities for which this will be able to do. But that's something to be done in the next few years. Yeah.
Hi, Leah Morabito from Durham University. Very nice talk, Pallavi. Thank you. For your obscured quasar sample, does the morphology match up with the spectral curvature? So you have unresolved and resolved sources, and then you have curved spectra and power law. Are the power laws, do they match up with the resolved sources, or?
Yes, in most cases they do. That's a good point that I haven't mentioned. That the power law that you see are almost all of them are well extended and likely to be older sources. There are a few compact sources which show power law, which I'm not sure why, but for at least for power law, all of them are extended, but there are some interesting compact sources for which I don't see a curvature which I would expect, or a turnover. So yeah, in one case it works, in another case it needs to be figured out. Cool.
We're gonna finish with a question from online. So Ilse van Bemmel asks, could SKA VLBI help to identify the structure of fainter and very compact sources?
Yes, yeah, this is something that I didn't include, is the VLBI capabilities of SKA. But yes, definitely, that's going to be, I need to do these calculations, which I didn't get to it. But yes, definitely, a fainter population would be definitely easily doable and in resolving the morphologies with SKA, with the VLBI capabilities. Yeah.
All right, okay, thank you very much.
Thank you so much.